if we remember with figuring out these three equivalent versions of our double angle formula for cosine. So if we write these down, we have cosine of 2a is equal to cosine squared of a minus sine squared of a. And this is also equal to 1 minus 2 sine squared of a, which is also equal to 2 cosine squared of a minus 1. Yeah, I doubt that actually. Hold on, let me double check before I keep going. Yeah, I just wanted to double check before I kept going and we somehow got everything wrong from here. Okay, so these are our double angle formulas for cosine. All three of these are equal to each other and are equal to cosine of 2a. But something really interesting is happening here. I have cosine of 2 times an angle is equal to something with sine of just the angle by itself. And also something here with cosine of just the angle by itself. Well, if I can go from something that doubles an angle to something in terms of just the regular angle, then maybe I can go the opposite direction. Maybe I can start with an angle if I know this angle, and then get something in terms of half of that angle, or vice versa. The idea is if we can double an angle, then maybe we can figure out how to take half of that angle. And, well, I wouldn't be talking about it like this if the answer was yes, we can. And that is why the title of this chapter again involves the half angle identity, or it says double angle, angle reduction, and half angle formulas. So let's look at these two equations and first get our power reduction formulas. So let's write out just the equivalents that we have for the second line. Cosine of 2a is equal to 1 minus 2 times sine squared of a. Well, now I can subtract 1 from both sides to get cosine of 2a minus 1 is equal to negative 2 sine squared of a. So now if I try and get rid of this negative, then on the left side, multiplying by that negative turns this into 1 minus cosine of 2a is equal to 2 times sine squared of a. And now I can divide both sides by 2 to get 1 minus cosine of 2a all over 2 is equal to sine squared of a. And this is what we call the angle reduction formula. I'm sorry, the power reduction formula, which is often abbreviated as just the reduction formula, which is not great because it's not very clear what you're reducing. But this is the power reduction formula. And if you just Google reduction formula, you're going to get some nonsense from calculus. So don't worry about that. These are called the power reduction formulas specifically. Well, why do we care about that? This takes something written in terms of sine squared and lets us rewrite it in terms of our trig function to a single power. Yes, the angle on the inside is doubled, but we no longer are squaring these trig functions, which right away doesn't feel incredibly powerful. And I would agree that it's maybe not. But we can take that a step further in a minute to get something that is pretty powerful. Well, the next one that we can do, the next reduction formula, involving cosine is if I look to the third equivalence that I have up here, and I consider cosine of 2a is equal to 2 times cosine squared of a minus 1. Well, I can do what I just did and solve for cosine squared. Add 1 to both sides to get cosine of 2a plus 1 is equal to 2 times cosine squared of a. And now I can divide both sides by 2 to get cosine of 2a plus 1 over 2 is equal to cosine squared of a. And perfect. That's what we would call the power reduction formula for cosine. Now, naturally, if we have one for sine and cosine, we can make one for tangent. So we can recognize that tangent squared of a is equal to sine squared of a over cosine squared of a. Well, if I can reduce the power for sine into 1 minus cosine of 2a over 2, and I reduce the power for cosine to cosine of 2a plus 1 over 2, then I can keep change flip, and once I get rid of the 2's that pop up, we'll divide by 2 here, and then it would turn into multiplying by 2 up there. And once you do that, it ends up simplifying to just 1 minus cosine of 2a over cosine of 2a plus 1. So this is our power reduction for tangent. Now, I think it's worth staring at these for a second, maybe. And we notice, well, I think we notice. Let me clear these things up. So now we're looking at our power reduction formulas. I think there's something interesting happening here once we look at just these. So let me maybe make this look a bit nicer. So once we focus on these, did not grab everything there. Eraser is very silly. Okay, so once we focus on these three power reducing formulas, power reduction formulas, then I think we outright see something incredibly interesting from how these are written. I start on the right side of these equations with only 1 times an angle. And what I plug in to the left side is 2 times that angle. So if I have something like sine squared of 15 degrees, I don't know what sine of 15 degrees is, but this formula says this should be equal to 1 minus cosine of 2 times 15 degrees, all over 2. And maybe we recognize 2 times 15 degrees is 30 degrees. So really, this gives us a very direct way to go from some angle to double of that angle. So starting with an angle and then doubling it lets us find half of angles that we don't know. So the idea is if I know what x is, if I start with x and this gives me something in terms of 2x, then all I have to do is understand 2x, and that gives me the x that I started with. So maybe I'm over explaining this, but maybe it's better to look at the equation that I came up with just to see, yeah, all I need to know is cosine of 30, even though I don't know what sine of 15 is. Now there's a small, maybe it feels like an issue here in that we don't have just sine of 15 degrees here. We have sine squared of 15 degrees. Well, how do we deal with a square root? Sorry, how do we deal with a square? We just take the square root of both sides. But the thing that we have to remember is the plus or minus that may pop up. So if I say on all three of these equations that the right side is squared, then when I take the square root of both sides, I have the exact thing on the left with a big square root and a plus or minus out front. So in class, I reiterated a few times the angle reduction, sorry, the power reduction and the half angle formulas are almost just the exact same thing. And that's because as much as sure we in some sense started from the angle sum identities here, we still had to do a lot of work to get to this point exactly. But comparing the half angle identities that I'm writing down right now to the identities at the top, there's not really any extra work that you have to do beyond just squaring or taking the square root of both sides. I think these are pretty immediate results of each other. Right, if I say solve for sine squared right here, you know to take the square root of both sides to immediately just get this. And vice versa, if we have this one, then I say get rid of the square root, square both sides, then you immediately get back up to here. So again, I think they're pretty straightforward in that sense. Okay, so now we used our angle reduction formulas to get to our half angle formulas. And now there's a really interesting conversation that comes up here out of trying to figure out whether we should be positive or negative. Now, the book almost makes a assumption. So let's move all of these great ideas up here. Now, the book says, look at the unit circle. And let's say that our angle theta is between 0 and 2 pi. Well, if theta is between 0 and 2 pi, then that really helps us figure out exactly what half of theta is. So if theta starts out in quadrant 1, then when I break theta in half, the biggest theta normally could be, if it's in quadrant 1, would be pi over 2, which means the biggest theta over 2 could be, if I divide theta in 2 in half, then the biggest it could be now would be pi over 4. So we were in quadrant 1. Now, well, we're still in quadrant 1. But what if we were in quadrant 2? Then the biggest theta could be would be pi. And the smallest it could be would be pi over 2. Well, once I divide that by 2, then now the biggest we were is pi. Then cutting that in half to get pi over 2 means that we're now between pi over 4 and pi over 2, which means we are still in quadrant 1. So if theta was in quadrant 1 or in quadrant 2, then now half of theta must be in quadrant 1. Now, if theta was in quadrant 3, then maybe we can tell what's about to happen. The biggest it could be would be pi, 3 pi over 2. which once we cut that in half, the biggest theta over 2 would be 3 pi over 4. But this is in quadrant 2. And similarly, if theta was in quadrant 4, the biggest it could be is 2 pi. So once we cut that in half, then the biggest theta over 2 could be is pi. Pi over 2 divided by 2 is pi. I'm sorry, 2 pi. Sorry, 2 pi divided by 2 goes to pi. So to that end, if we know that we're between 0 and 2 pi, or 0 and 360 if we're degrees, then when I cut theta in half, I know exactly what quadrant we end up in, as long as I knew what quadrant we started in. So we do get to make a lot of smart decisions there. Now, where this starts to not be so trustworthy is if we pretend, or not pretend, if we don't know what range of values theta is in. So let's say, take for instance, this example that we talked about in class with 714 degrees. Well, let's ask ourselves what quadrant 714 degrees is in. Well, I don't know what quadrant exactly that number sits in, but I can go to my calculator and I know that I can subtract 360 from this to get something coterminal that I am better at telling you what quadrant it's in. So 714 minus 360 turns out to be 354 degrees. Okay, well, what quadrant is 354 degrees in? That's in quadrant 4. So 714 degrees is in quadrant 4, because again, it sits in the exact same spot as 354. Well, so I know 714 degrees sits in quadrant 4, which means if we made the same assumptions or if we pretended like we made the same assumptions like with the other situation of cutting the angle in half, and that puts us in quadrant 2, then I would think right away that half of 714 must be in quadrant 2. But if we go to our calculator and type in 714 divided by 2, we see that actually half of this angle is 357 degrees. And is that in quadrant 2? No. This is still in quadrant 4. So this is just an illustration that you get to know exactly what quadrant you end up in if you know what range of values that your theta had to be. So if you know that theta is between 0 and 2 pi or 360, then yeah, knowing the quadrant does help you a lot. But if you don't know what range of values that your angle is in between, then you can end up in any possible quadrant. Because here's just an example where the angle is in quadrant 4, but even half of the angle is in quadrant 4. But generally speaking, on the exams and worksheets and whatnot, I think we are given this assumption. And on the homework, they do tell you like a specific range of values that you are between. So if you know where theta is, then you know where theta over 2 is, because you can just cut those in half. If theta is between 0 and 2 pi, then just divide everything up there by 2, and theta has to be between 0 and pi. And you get to make those informed decisions from there. Very good. But at the end of the day, we get these 3 formulas, which are very powerful. If I know what an angle is, if I know what 2a is, then I know what A is. So because I know what 45 degrees is, I know what half of 45 degrees is, and so on and so forth all the way. And so, again, the consideration of whether or not we're going to be positive or negative is going to be based on the rest of the information from there. Again, how do we know whether sine, cosine, or tangent's output are going to be positive or negative? Well, that's based on what quadrant we end up in. Very good. Okay, so that is pretty much where this chapter ends for us. So very good. Goodbye.